Hello, this is Group Flap AI, and my name is Dili Malati.
My name is Princeton.
And my name is Josh Capelli.
A quick overview for our project. We recreated the classic mobile game Flappy Bird, as well as design and implementation of our own hard mode with additional features. We also been training ML Agent to play both game modes that we have been developing through the ground up. In terms of game development, we have been utilizing Unity Game Engine for the core gameplay and UI features. And for the machine learning development, we have been utilizing the ML Agent Toolkit as well as our own handwritten machine learning algorithms, such as Q-learning.
So as far as UI and game state goes, which is my one of my responsibilities, not much has changed since the last time. It's still just a basic Flappy Bird UI. You see like the start screen, which has the easy mode and hard mode. You have like some tutorial screens for easy and hard mode, and then you have the game over screen, which takes you back to the beginning. We can see the yeah. So here's like it's an example of the code for like changing states and have the states stored, which is like through an enum at the top. And we also have like a scoring system there, and the game saves your high score to the locally to the machine. And if your new score is higher than the high score, it just replaces that. And we also have here's like an example of the medal system. So when you pass certain score thresholds, it'll give you a bronze, silver, gold, and platinum medal, just like in the original game, and that'll show up on the death screen.
So I was in charge of the original mode, and within the original mode, uh, I was in charge of making the player controls, so flapping or not flapping, the collision system with the pipes and ground, the animations of the bird, the game's logic, the user interface, and the scoring that you can see across the different playing sessions. So to the right is an example of our game. And here's some code that shows how the user input was handled, how the player would move and rotate, along with how the bird would rotate as well.
Uh, I was in charge of the hard mode development that includes the shooting action with its collision and cooldown, the special closed pipe, such as the gravity reversal, extra life barrier, and shrinking mechanism. I also created the collectible in the game. As you can see on the demo on the right, there's coin in the levels that will be increasing the player score upon collection. And here is the code in the spawn class that handles the closed pipe spawn logic based on the random value assigned. Here is the bullet spawner class that handles the shooting action by taking in user input as well as the shooting cooldown. And here's the bullet class that handles the collision between the bullet and its environment. And lastly, this is a series of code that handle the player interaction with the environment and collision within its level.
All right. So one of the ML agents features that we've already gotten to work pretty well is the easy mode. So you can see a video for here in action. On the left, you can kind of see the raycast system, which just tells the player like what's in front of it. And then on the right, you can see what the actual player sees. And the agent also receives information such as the position of the pipe closest to the front of it, as well as its Y velocity. All right. So you can see here some examples of the code and the implementation. On the middle left, you can see like the behavior parameters that's provided by the library. So like the space size of like the observation vector, as well as like the decision period, which is like how many frames it takes to make a decision. On the right, you can see some code for like collecting observations. So that's just how it gets information about its environment, as well as how it converts a decision to an action such as player.jump. And then on the bottom left, you can see an example of the tensor board, like cumulative reward, this is the episode length period. And you can see these spikes here on the left because we use a curriculum learning system where it first learns how to play without any pipes at all. And that's like the first spike of how well it does. And then it goes down because it reduces the it adds pipes and makes them pretty wide. And once it gets good at that, the pipes just get narrower and narrower until eventually on the last stage, which is stage 7, where it just finally stops being spiky. That's when it goes to the normal pipe width that it plays with the game.
For the Q learning, We have a type of reinforcement learning algorithm that enables the agent to learn how to act optimally. So for the project, we first had to define the state space and the action space. So those are corresponding to the game and the different actions that the player can take at any given moment. We then initialize a table containing all that information, which we call a Q table, and then we observe the current state. Then we take a certain action based off the best possible actions and our greedy hyperparameter, which will be given a certain probability based off if we would rather explore or just choose the highest Q value rating. We'll then execute the action, observe the next reward, and update our Q table.
And we are also been working on the ML agent hard mode implementation, as you can see on the screenshot here. Um, Different from the easy mode, we have been adding more observation for our AI agent that include the closest coin and other collectibles, as well as the close pipe location. We also added one more action that the AI could perform beside from the jump that it automatically does. We also added the shooting action for the AI, and we are also rewarding the AI agent not only through the pipe pass through, but also through the coin collections throughout the levels. And lastly, we end the training episode upon the collision with the ground or obstacles, and we will start the new training process. And here's just a series of code that we use to handle the closest pipe position and coin position. And here is in the same class where in the update function, we call the function on each frame where it handles whether or not the pipe or the coin has passed through the player. So we will not be feeding that information into our AI agent. And lastly, the on episode begin function will be called on every single new training episodes where it will resetting the score, the position for the player, the velocity, as well as other various type of environmental variables throughout the levels.
All right, so as far as future milestones go, as we just mentioned, we have the emulations hard mode training. This will primarily be Dylan Maladi's job, and this involves like the Gale-based training as well as like the extra observations. But that's like largely like complete, but we still do need to actually train it. Next, my primary responsibility will be DQN. So this is like an outside library algorithm that involves taking like a pixel array of input data, so just like the RGB values on the screen, albeit with a reduced dimensionality, and just training off that. Although it might take a very long time to train comparatively because it's not as like fancy, I guess, and it's just a little bit tougher for the thing to learn. And finally, we have the NEAT algorithm. This will be Joshua's primary responsibility. This involves initializing a population of simple neural networks, and then much like the way evolution works in like real life, it'll like repeatedly select the fittest networks to reproduce, introduce mutations, and occasionally it'll cross over parts of different networks to create offspring to combine the abilities of two networks.
So for our static analysis, we have used branch protection. With the branch protection, we basically have code that automates our testing, which you can see in the top right picture with the three different testings in edit mode, play mode, standalone mode. And it then basically creates a Windows software executable, just so that we know we have clean and precise code.
And lastly, one of the bigger issue that we have been encountering throughout the development process is our ML agent was not getting properly rewarded for getting through the checkpoints or the obstacles. As you can see from the screenshot on the top right, although in the imitation recordings, the AI seemed to be rewarded properly through the pipe passes, but on the actual training process reflected from the tensor board here, as you can see, the cumulative reward it's a constant zero, which implies that our agent is not being rewarded for passing through the pipes. We will be keeping a close eye on this issue and trying out a different method to train our AI to make sure it's properly implemented and have better performance. And this is end of our presentation too. Thank you.
Thank you.